Okay, so this is our problem session number 2, and I've posted these questions as well as the solutions on my webpage already, and then I'm going to put the videos up there as well. So yeah, you guys can get nice and cozy here, plenty of room. So these are the problems that I was going to practice with you guys. There's a copy of the sheet here, and yeah, so these are mostly dealing with the concept of limits of functions. This is chapter 4 that we've been talking about. So I have some examples here. So let's look at the first problem. First one is just a very standard example, but it's just good for practice, okay? So number 1 just asks us to prove that the limit as x approaches 3 of 1 over x squared is equal to 1 over 9. And they want us to do this directly from the definition, because of course you could use the limit theorems. You could use the limit theorems. The limit of the top is 1, the limit of the bottom is just 3 squared, and then you get 1/9. But they want us to actually use the epsilon delta definition. So of course the way that works is we're going to start by letting epsilon greater than 0 be given. And then we have to kind of do some scratch work to figure out what the delta is, right? So maybe I should just remind you over here, I think everybody knows this already, but just so we have it on the board, the limit of f of x equals L as x approaches c just means that for all epsilon greater than 0, there exists a delta greater than 0, and if 0 is less than absolute x minus c is less than delta, then absolute f of x minus L is less than epsilon. Right? That's the definition. Okay, so we're going to use that. So our job is to cook up a delta, and we want f of x minus L to be less than epsilon. So let's just write down what that would look like. So if I think about this as scratch, real fast, we'd have f of x is 1 over x squared, right? And the L is 1/9. And we want this to be less than epsilon. Okay? So we want to end up somehow with this thing being less than epsilon at the end of the day. Agreed? Mm-hmm. Okay, so what would you suggest I do in terms of the scratch work here, working backwards? Get a common denominator. Very good. So the common denominator would be 9x squared, right? So then we would just get a 9 and then minus x squared, right? Less than epsilon. Agreed? Mm-hmm. Okay, and now what could we do next? Keep in mind, you want to be looking at, you want to try and extract the x minus c. What is the c here?
The 3.
C is 3, so we like to get x minus 3. Can we get that from this somehow? Yeah, if we factor the top, I can get x minus 3 times x plus 3, right? Over, and actually I don't even need to put the absolute value bars around 9x squared, because that's always going to be positive anyway, right? So I get something like that. Okay, now, the x minus 3 is fine. The rest of this expression, of course, still has the x's in it. So I could try and extract exactly what x minus 3 is less than. So it would be 9x squared over absolute x plus 3 times epsilon, right? So that would be, so far every step we did here is reversible, okay? Now, what I'm going to suggest is that we're going to do a step that only works backwards. You remember that the steps always have to work backwards. They don't have to work forwards. And it will work backwards as long as I replace what's on the right-hand side with something that is bigger. So something that is smaller. Because if x minus 3 is less than something that is smaller than this, then it will be also less than this by the transitive property. So what I'm going to do, though, here first is I'm going to restrict the x domain a little bit. We've seen this idea before, right? The idea here is I'm going to choose a preliminary delta. Okay, so does anybody have a suggestion for a preliminary delta here?
1.
1. Okay, great. If I choose a preliminary delta of 1, then we will only be looking, we know in the future when we actually write the proof, we will only be looking at x's between 2 and 4. Now on that interval, what I'm going to do is I'm going to make this right-hand side smaller. So what's the smallest that I can make it? Well, the way that I make this smaller is I make anything in the numerator as small as I can, and I make the denominator as big as I can. This is a case where I'm going to choose the 2 for x on top, but I'm going to choose the 4 for x on the bottom. Of course, in real life, x is not going to be equal to 2 and equal to 4 at the same time. But what we're doing, we don't have to worry about that. We just have to come up with a number here that will be smaller than what this actually is. So I'm going to replace this with 9 times 2 squared over the absolute value of 4 plus 3 times epsilon. So that actually becomes 36 over 7 times epsilon. Does everybody understand? The reason I like this example is it shows with numerators and denominators, how do you decide which endpoint to replace with, right? You're choosing the 2 on the top to make the numerator smaller, but you're choosing the 4 on the bottom to make the denominator bigger, so that the whole fraction is smaller now. Okay? So then, when we go over here, we're ready to write our actual proof. We choose delta to be the min of 1 and 36 over 7 times epsilon. Okay? That look all right? So now, if we were gonna, I'm not gonna write the whole proof forward out here, but if we assume now, if we assume that 0 is less than x minus 3 is less than delta, so I'm just now checking, I'm checking that delta works right here. Now we actually have to run the proof forward. Okay. So assuming that, then we know, for example, that x minus 3 is less than 1. Because delta is at most 1 here. So 2 is less than x is less than 4, right? And the absolute value of x minus 3 is less than 36 over 7 times epsilon. So we have this statement here, which is where we're at the bottom of the board, right? And given that x is between 2 and 4, I can make x a little bit bigger and on top and make it a little bit smaller on the bottom to make, make x a little bit bigger on top and a little bit smaller on the bottom to make this right-hand side even bigger, right? So now, absolute x minus 3 will be less than 9x squared over absolute x plus 3 times epsilon. Okay? Does that make sense? And now we just run the steps backwards. From there, everything is reversible. Okay? So now, retrace scratch work in reverse to get absolute 1 over x squared minus 1 over 9 less than epsilon. Okay, so that's how that works. You getting comfortable with these arguments?
Can we say this statement in exam?
Yes, absolutely. Retrace the scratch work in reverse, as long as you have connectives here. But one thing people I see people just writing statements with no connectives, and I need to know what steps are going forwards and which ones are going backwards.
So in principle, you can choose any positive preliminary delta, right?
Yeah, the delta could have been anything. I would recommend that you choose it here to be something smaller than 3, because if the delta was more than 3, then your interval, your x range would include negative numbers, and that's going to get a little bit tricky, because now when you're trying to make the numerator as small as possible, you actually have to put 0 for x. We don't want to do that, because then you've got a 0 over here and you sort of wipe out the right hand. So you get something that's basically impossible. Right, so you don't want x to be able to be equal to 0. So don't choose this delta bigger than this value here.
Is that like a rule for,
yes,
for just choose delta not just less than c?
Right. Choose delta to be, so if you have c here and 0 here, sometimes I use c over 2, right? But if it's a specific number like 3, I can just get away with delta equals 1. But yeah, it doesn't matter too much. There's more than one right answer here. But just try not to include 0 for the x there. Okay? Does everybody feel like they could do those kind of problems? Yeah, it's not too bad? Yeah. Okay, great. All right, let's take a look at the second one then. The second one's really pretty easy as well. So number 2, this says, so we have a domain D is a subset of R, and C is equal to an accumulation point of D. And then assume that the limit of f of x as x approaches c, assume that that is equal to L. And then we're going to prove that the limit as x approaches c of the absolute value of f of x is equal to the absolute value of L. Okay, so in other words, limits respect absolute value. Okay, this is something you may in the future want to use sometime. Okay, you're allowed to use this one. Okay? Make sense to everybody? Seem reasonable? Okay. So let me get this out of the way. Think about how we would do this. We still have our definition up here, which we can take advantage of. So to prove that the limit of one thing is equal to another thing, we just use our epsilon delta definition, right? So the proof would start out with what would be the first sentence?
Let epsilon be good.
Good. Let epsilon greater than 0 be good. Okay. And then we need to figure out through the scratch work how to pick the delta. Okay. So working backwards again, so I'll just call this scratch. We want to have what? The absolute value of f of x minus the absolute value of L. We want to look at this difference. Okay? And we want that to be less than epsilon. Okay? And we know that if we have the absolute value of f of x minus L less than epsilon, then there will be a delta for that, right? There is, because this limit already is assumed.
Mm-hmm.
So given this epsilon, there already exists a delta, so let's just maybe note that now. Okay, so let me just say it now. So since, I'll go back up before the scratch work. We'll just add this at the beginning here. Since the limit of f of x is equal to L, right, there exists already a delta greater than 0, such that if 0 is less than absolute x minus c is less than delta, then absolute f of x minus L is less than epsilon. Okay, so we have that. And then this is what we want to get.
We use the triangle inequality.
Yeah, we have a proposition, or actually I think it's I have it here. It's a corollary back in chapter 2 that says, so I'm just going to recall for you what it says. There's a corollary that says if you take the absolute value of the difference of absolute A minus absolute B, so if you take the absolute value of those two things, that's less than or equal to just the absolute value of A minus B. So the difference between 2 points can only get smaller if you take their absolute values. Okay? So actually, if we already have found a good delta that makes this one true, and we want this one to be true, what can we do?
So we can rewrite.
I don't think I need the scratch work. I'm just going to go continue the proof here. So we already have our delta that makes this inequality true, and we want this inequality to be true. So do you see it?
Yeah, just use the second one.
This
That
thing,
one.
right? Yeah, exactly. So if I claim this is already true.
Yeah.
I don't have to change my delta at all, right? I just simply put in absolute f of x minus absolute L, absolute value of that whole thing. That's already less than or equal to the absolute value of f of x minus L, which is less than epsilon, as needed. So the same delta the same delta works. So actually really easy proof.
Yeah.
That's a really, really simple one. Okay, does that make sense? Everybody good on that? That for you. Sure. Okay, so that's a nice little problem. So this is one that's worth remembering. You can take absolute values of expressions, and this is not a problem. Okay, can I erase this one? Okay, good. We're moving right along here. See how these next ones go. Okay, the third one has to do with a limit at infinity. So we talked a little bit about this this past week. So number 3, let's suppose I did ask you to compute the limit as x approaches infinity of 2x squared minus 5x plus 6 over x squared plus x plus 1. So what I'm going to do is erase this limit definition and put in the one for infinity. Okay, so this is one that you should be putting onto your flashcards, I think. So the limit of f of x equals L when x approaches infinity. What is this definition? This just means that for all epsilon greater than 0, there exists an alpha greater than 0, right? Such that if x is greater than alpha, that implies that absolute f of x minus L is less than epsilon. So this is we did this in class the other day. Okay? So that's the definition we're going to work from. We really don't have anything other than a definition. Remember, guys, we don't have limit theorems for x approaching infinity, at least not yet. And at some point we could prove those things and then we can use it. But for now, this is all we have. Okay. So the first thing to do is to figure out what you think the answer is and then try to prove it. So as x gets really, really, really big, what do you suspect that this limit will equal?
2.
Right, the leading terms are going to be, basically it's of the order of 2x squared over x squared, which is going to be equal to 2. Does this make sense? So now we have to try to prove that using the definition. Exactly, so the L is 2. Okay, so proof. And what's the first sentence?
Let epsilon be greater than 2 given.
Good, let epsilon greater than 0 be given. Exactly. Start all of these problems the same way. Okay, and our job is to come up with an alpha. Such that if x is greater than alpha, the absolute value of f of x minus L is less than epsilon. So let's look at our scratch, another problem where we need to do a little bit of scratch calculation. So the f of x, I'll put that here, 2x squared minus 5x plus 6 all over x squared plus x plus 1 minus L, which is 2. Right, and I want that to be less than epsilon. Okay. What I'm going to actually do, before I start doing a chain of biconditionals, let me just simplify this first. The algebra simplification is, of course, reversible. So, in other words, I can just go ahead right now and put down a common denominator of x squared plus x plus 1. And so that's going to give me 2x squared minus 5x plus 6 minus 2x squared minus 2x minus 2. Right? So I'm subtracting double the denominator. Okay? Is everybody with me? Yeah. So I'm just doing the algebra here. Now if I simplify that, I'm going to get 4 minus 7x on top and x squared plus x plus 1 on the bottom still. Okay. And what I'm going to do, I'm going to rewrite that as 7x minus 4. I'm just switching the order of the top, and I can do that. I can do that. Now, as long as our alpha as long as our alpha is at least 4/7, I don't need the absolute value bars on anything here. Now, remember guys, we're going to choose the alpha. So I can always choose it to be, you know, a maximum of either this one or something else, right? So I can ensure that this will be true so that the only x's that we will ever look at will be greater than 4/7. So I will be able to make that happen so that I really won't need the absolute. These absolute value bars are not necessary if x is bigger than 4/7. So I'm going to make sure that x is bigger than 4/7 when I get around to writing my proof.
But how did you figure out that alpha must be greater than 4?
So I just set the top equal to 0.
Oh, okay.
Just to make sure that the numerator was not negative, I figured out where does it switch from negative to positive. So it switches to positive right at 4/7. Okay. Everybody with me? So really, what we want is we want that to be less than epsilon. So now I'm gonna actually write that down again. 7x minus 4 over x squared plus x plus 1 less than epsilon. And I am going to give you a backwards step. We only need the steps to work backwards. If I can make this bigger, the left side bigger, and if that is less than epsilon, then this will be less than epsilon. As it stands right now, you would be challenged to solve for x, right? You're trying to solve for x in terms of epsilon to figure out what should your alpha be. You're going to be challenged to solve this one for x. So before I do that, I'm actually going to make this simpler first, and then I'll solve for x, right? So the question is, well, how can I make this simpler? Well, one thing is I can make the numerator bigger. Let's just make the numerator bigger. Let's not subtract 4. Let's just make it bigger, right? And I want to make the denominator smaller, right? And the smaller thing I could choose for the denominator would just be x squared, right? Just drop off the lower terms. Okay, does that make sense? Okay. So I made the numerator bigger and I made the denominator smaller. If this is true, then definitely this is true because I just made this fraction smaller. Right? And of course this one is just 7 over x less than epsilon. See, now I can solve for x very easily. X is greater than 7 over epsilon. Right? Does that make sense? X is greater than 7 over epsilon. We good with that? Okay, so what am I going to do to choose my alpha now that we've got this part solved? Right, the max of 4/7 and 7 over epsilon. Exactly. Okay, so I do that, okay. And then I'm going to just check that alpha works. So I'm going to assume that x is greater than alpha, and I'm going to show that absolute f of x minus L is less than epsilon. Well, if x is greater than alpha, then of course that means that x is greater than 4/7. So that was the point. This inequality here will hold as long as that's the case. And x is also greater than 7 over epsilon. Both of those things are true, because alpha was the max of those two expressions. Okay, so now working backwards, so now we basically work backwards through our scratch work. So reversing scratch, we get absolute value of f of x minus 2. So this is f of x minus 2. Is equal to 7x minus 4 over x squared plus x plus 1. In other words, I'm just ramming all of these equal signs into one conclusion. And now, because x is greater than 7 over epsilon, working this way, this is less than epsilon. And that's the end of the proof. Okay, so you're using your scratch work backwards now. The first line is just a bunch of equal signs, just to simplify it. The second line is where you have the inequality that gets you to where you can pick up over here and work backwards. Okay, so everything's kind of going in reverse. Make sense? Okay, so that's a good example of proving that a limit at infinity exists equals a certain value. We happy with that? Okay, great. Vanessa, did you get your homework back?
Yes.
Okay. Making sure. Okay, couple more problems here. Let's do number 4. Determine whether or not these limits exist and then give a proof either way. So the first one, part A here, is the limit as x approaches -2 of x cubed plus 7x squared plus 10x all over x plus 2. Okay, we'll have that as our problem. Notice that this is a rational function that is not defined at -2, but I'm only taking a limit as x approaches -2, so there's no problem with having a 0 on the bottom when you plug in -2, because that's not really what you're going to do. You're not literally going to plug in -2 on the bottom. Any suggestions?
I'm going to factor it out.
Okay, see if we can factor the top, okay? Let's just do that over here so it's not in the way. X cubed plus 7x squared plus 10x. Of course, I can take out an x. That leaves me with x squared plus 7x plus 10. And that then can be further factored, right? X plus 5 times x plus 2. Look okay? Okay, great. So let me just put that into here then. So we have the limit as x approaches -2. On the bottom, x plus 2, and on the top, x times x plus 2 times x plus 5. Okay. Okay, now what can we do?
You can cancel x plus 2.
Right, this may seem like this is too simple for Math 350. Like you feel like you can't do this. But remember that in this limit calculation, x will not ever have the possibility of equaling -2. So for the purposes of calculating this limit, x does not equal -2, and so you are literally doing high school algebra. You are literally just canceling something from the top and the bottom, and that there's nothing illegal about that you have to worry about. You can just do that straight off. Okay. All right, and so now you have the limit as x approaches -2 of x squared plus 5x, right? And how do you evaluate that limit? Plug it in. And when you plug it in, what are you really doing?
You're using the limit laws.
Exactly, we're using the limit theorems here. We're saying that limits respect addition, they respect scalars, they respect multiplication. So you're simply putting all of that in. 4 minus 10, which is -6. Okay, that's the answer. So there's no need here for an epsilon delta proof. They didn't ask you for that. So you can use, unless they tell you how to do the problem, you can use whatever tools you want. Okay. Everybody all right with that one? Okay, and then we have one more here. Part B, the limit as x approaches 0 of x plus 3 times the sine of 1 over x. This time, you can't factor and cancel like we did on the first example. If you plug in 0 for x, well, you already have a problem there. By the way, just for my curiosity, does anybody know what the graph of sine of 1 over x looks like? Of course, it's bounded between 1 and